Welcome back to another exciting video on matrices. In this video, I'm going to explain how to find the determinant of a 2 by 2 matrix and the inverse of a 2 by 2 matrix. Define the determinant. So first, what is a determinant? So in linear algebra, the determinant is a value associated with a square matrix. Okay, it's really special. It does a lot of cool things. It's just a way to kind of talk about it. It's very much like the discriminant with a quadratic. It tells you some cool stuff. So the determinant of a matrix A is denoted as det A, or bar A bar, which is kind of a weird way to go through and do it, but it is what it is. So in the case where matrix entries are written out in full, the determinant is denoted by surrounding the matrix entries by vertical bars instead of the brackets. So instead of this, it looks like this. The determinant can be computed from the entries of the matrix by a specific arithmetic expression shown below. So given a matrix like this, the determinant is AD minus BC. So if we look at that, A, B, C, D, and actually look and see what's going on there. Let me change the color to something more exciting. You're going A to D, D minus right here. So it's this like loop thing like this that you go through. And that works for all 2 by 2s, which is kind of nice. So let's practice doing this. So it's this little loop thing that you go through and do like so. So it's 1 times 2 minus 2 times 4. 1 times 2 is 2. 2 times 4 is 8. 2 minus 8 is negative 6. So the determinant of this matrix is equal to negative 6. Kind of nice. It's really not that hard, which you can be quick to do. You can probably do these in your head, but I'm going to write it out because it's always good practice. You can see if you make mistakes, really see what you did wrong. It kind of gets confusing with some of the negatives. Like there's a lot of negatives going on in these two things here. So this is 6. This becomes minus 5 times negative 1, so plus 6, and this is equal to 12. Okay, next set here. So I do 1 times negative 5 minus negative 5 times 1. This gives me negative 5 plus 5, which is equal to 0. And earlier I mentioned how it's kind of like the discriminant with a quadratic. Well, determinants of 0 are interesting and give you some properties and all that kind of fun stuff. We'll see that eventually, probably. Okay, 4 times negative 2 minus 3 times negative 3. Okay, so put this together, I end up with negative 8 plus 9, which is equal to 1. Okay, so finding the discriminants are not all that bad. Pretty quick to do. Nothing really all that exciting. Let's move on. So inverse of a 2 by 2 matrix. So we talked about the identity matrix. I is equal to 1, 0, 0, 1, or there's just 1's on the diagonal and then 0's everywhere else. So the inverse of the matrix A is defined as A inverse, such that A times A inverse is equal to A inverse times A, which is equal to I. And the other day we saw that when you multiply matrices, A, B does not necessarily have to equal BA, except for certain situations that pop up. And this is really important that you guys remember this. Matrix multiplication is not necessarily commutative, but to have an inverse, it has to be commutative. If it isn't commutative, then it's not an inverse. So only square matrices can have an inverse because all identity matrices are square matrices. So that makes sense. So given a matrix here, then the inverse of the matrix A is A inverse, and it's 1 over the determinant of A times D negative B negative CA. So this gets a little bit interesting. Okay, not that bad. It's just a formula to remember. You guys can do it. I believe in you. So let's go through and do that. So remember, this is A, B, C, D for my basic matrix. Let's make that more like a D. Let's find the determinant. So det A is equal to negative 2 times negative 4 minus 2 times 5. And this all put together becomes 8 minus 10, which is equal to negative 2. So my determinant's negative 2, so you got 1 over negative 2 times the matrix, and then you have to flip everything. So D, which is negative 4, goes first. And then you do negative B, so flip the signs of the two diagonals. So it's negative 2 and then negative 5. And then take A and put it in the corner. And this is your inverse. You can either choose to leave the determinant out like this, or you could put it inside. In general, I kind of like to put it inside because it makes checking that it actually is an inverse a little bit better. This is A inverse. Okay, so let's put it inside. This becomes negative 1/2 times negative 4 is 2, 1, 5 over 2, and then 1. And there's your inverse matrix right here. We could check, but I won't. You guys can do it. Okay, so let's go through and do the next one. So 3 times 6 is 18, minus 9 times 2. So 18 minus 18 is 0. So the determinant of n is equal to 0. Now that means there's no inverse, because 1 over 0, it's undefined. So no inverse. All right, moving on. All right, same process here. 4 times negative 4 is negative 16, minus 8 times negative 2, which is negative 16. Oh, that's equal to 0. Okay, so the determinant of P is equal to 0, which means no inverse. Okay, these are actually kind of rare to have no inverse, but it could happen. You always have to check. It's really important. Okay, this one, let's try this. So negative 1 times negative 2 minus 2 times 0. Okay, so that just goes away, and it's just 2. Okay, so my determinant is equal to 2. So the determinant of O is equal to 2, which means my inverse is 1 over 2. So O inverse is equal to 1 over 2 times, so remember, it's flip your diagonal, your main diagonal, so negative 2, negative 1, and change the sign here and here. 0's never negative, so that's it there. Okay, then we want to go through and distribute that 1/2 as a scalar, and this becomes negative 1, negative 1, 0, and negative 1/2. And that's how you find determinants and inverses of matrices, specifically 2x2s. 3x3s get a little bit wacky. We'll see those in another video. Thank you guys for watching, and please make sure you subscribe down at the bottom so you can get all the updates for my channel.